You know, Alex, they say light is the best disinfectant, but in my shop, it usually just highlights the gaps in my joinery that I was hoping the finish would hide.
Well, if you'd stop building in the dark like a Renaissance hermit, maybe those gaps wouldn't be there in the first place.
Hey, there's a certain romance to a single flickering bulb, but lately, I've been bitten by the LED bug. I tried to put some under cabinet lighting in the kitchen last week. I figured, how hard can it be? It's just sticky tape with tiny suns on it.
Oh no, I recognize that tone. That's the tone of a man who accidentally turned his kitchen into a strobe light disco or smelled something melting. Which one was it?
Neither, actually. I got it all wired up, hit the switch, and the first 3 feet were blindingly white, while the last bit looked like a dying ember from a campfire. It was like the electricity just got tired halfway through the run and decided to take a nap.
You ran into voltage drop. You're a master of timber, Tiger, but electrons don't follow the same rules as wood grain. Today, we are talking about the Tiger Den Guide to not burning your house down with LEDs. We're diving into power calculations, types of diodes, and why your lighting projects might be gasping for air.
It really is a different world. When I started out, a light was a glass bottle with a wire in it that got hot enough to cook an egg. Now we're dealing with electroluminescence. You've got these semiconductor chips, usually gallium arsenide or something that sounds like it belongs in a sci-fi villain's lab. And when you shove a current through them, they spit out photons.
And unlike those old incandescent bulbs that were basically 95% heaters and 5% light sources, LEDs are incredibly efficient. But according to these technical specs from Analog Devices, that efficiency comes with some inherent peculiarities.
That's engineer speak. For if you treat it like a light bulb, it will die. Take standard red or green LEDs. In the old days, we'd just slap a resistor on there to stop the thing from eating too much current and popping like a tiny firework.
Right, because LEDs are current hungry. They'll try to pull everything the power supply has until they literally cook themselves.
Exactly. I remember building a little status light for a dust collector remote. Simple red LED. I didn't bother calculating the resistor. I just grabbed one that looked about right from the bin. The LED was a glorious, brilliant crimson for exactly 3 seconds. Then it turned a sickly shade of purple, let out a tiny puff of magic smoke, and that was the end of the show. I basically paid a 3-cent tuition fee for that lesson.
Only you would find a way to make a red light go purple. But that's the basics: forward voltage and forward current. For the simple stuff, like those 5mm diodes, the voltage drop is tiny, maybe 2 to 3 volts. But when we move into the projects our listeners are doing, shop lighting, accent strips, smart home setups, we aren't just dealing with a single diode anymore. We're dealing with meters of the stuff.
And that's where the math starts to bite back. If you're looking at these LED strips, the first thing you have to look at is the nominal power, the watts per meter.
I saw a great breakdown on this. If you have, say, a 3-meter strip and it's rated at 4.8 watts per meter, you're looking at 14.4 watts total. Easy, right? But if you buy a 15-watt power supply, you're asking for a bad Saturday night.
You're redlining it. It's like trying to drive your old farm truck at 100 miles an hour for 10 hours straight. It might do it for a minute, but eventually something is going to start screaming. The rule of thumb I've learned, usually after a power brick gets hot enough to soften the wax on my workbench, is the 20% margin.
20 to 30% to be safe. So for that 14.4 watt strip, you really want something around 18 or 20 watts.
It keeps the components cool. Heat is the silent killer of electronics. It's not like a wood joint that might shrink over 20 years. An overheated LED driver will just give up the ghost right in the middle of a dinner party, leaving you and your guests in the dark with a faint smell of toasted silicon.
Let's talk about the big mistake people make with volts versus amps. I've seen people try to plug a 12-volt LED strip into a 24-volt power supply because it has more power, only to watch the strip turn into a very brief, very expensive fuse.
Oh, I've done the opposite. Plugging a 24-volt strip into 12 volts. It's like trying to run a marathon while breathing through a cocktail straw. You get this pathetic, ghostly glow that looks like a haunted house effect you didn't ask for.
So, the formula: watts equal volts x amps. If you know you need 100 watts of light and you're running a 12-volt system, you're pulling over 8 amps. That's a lot of juice for thin little wires.
And that leads us back to my kitchen disaster, the voltage drop. When you have low voltage, like 12V, the resistance of the actual copper on that thin LED strip starts to matter. By the time the electricity gets 10 feet down the line, it's lost its gumption. It's like a garden hose with too many leaks. The pressure at the nozzle is just a sad little dribble.
So, how did you fix the kitchen? Or is it still half lit?
Don't tell my wife, but it stayed half lit for 3 days while I researched. The secret is power injection. Instead of just feeding the electricity in at the beginning of the strip, you run a separate, heavier gauge wire alongside it and inject power at the end or even in the middle.
It's like having a second pump for that garden hose halfway down the yard.
Exactly, it evens everything out. The colors stay consistent, especially with those RGB strips. Have you ever noticed how they turn red at the end of a long run when they're supposed to be white?
Because white requires all three colors, red, green, and blue, to be at max power. If the voltage drops, the blue and green diodes, which need more push to stay bright, give up first. Red is the low-energy, lazy sibling of the LED family. It'll keep glowing long after the others have quit.
It's poetic in a way, but a nightmare if you're trying to build a clean-looking shop light. Now, let's talk about the luminaires. That's the fancy term for light fixtures that people who wear lab coats use. When you're calculating the load for a whole room, you can't just add up the LEDs, you have to think about the driver.
That's the box that converts your 120-volt wall power into the DC juice the LEDs crave.
Right? And those drivers aren't 100% efficient. They have a power factor. If you have a 300-watt fixture, it might actually be drawing more than that from the wall. If you're planning a big shop renovation and you're putting 20 high-power LED bays in, you can't just assume they'll run on a single 15-amp circuit just because the math on the box says so.
Especially since lighting is considered a continuous load.
Exactly. The National Electric Code, which is a book written in the blood of people who didn't listen, says if a light is going to be on for more than 3 hours, you should only load that circuit to 80% of its rating.
So a 20-amp breaker is actually a 16-amp breaker in the world of shop lighting.
You got it. I once saw a guy try to run his table saw and his entire new LED array on the same circuit. Every time he pushed a piece of oak through the blade, the lights would dim just enough to make him think he was blacking out. Not exactly a recipe for shop safety.
You mentioned smart LEDs earlier. Those seem like a whole different beast. It's not just a light anymore. It's a computer that happens to glow.
Those WLED projects are all the rage. My nephew built a cloud for his ceiling using polyester stuffing and addressable LEDs. Each little diode has its own tiny brain. But man, those things are thirsty. A single addressable LED can pull 60 milliamps at full white. You put 1,000 of those in a room, and you're looking at 60 amps. You could practically weld with that kind of current.
I can see the headline now. Man accidentally vaporizes living room trying to mimic a thunderstorm.
It's a real risk. People see these tiny wires and think, oh, it's just LEDs, they're low power. But 5 volts at 40 amps will melt plastic just as fast as 120 volts will.
So, for someone listening who wants to start their first real LED project, maybe lighting up their workbench or putting some accent lights on a bookshelf, what's the Tiger Gold Standard workflow?
First, don't buy the cheapest stuff on the slow boat from overseas unless you like the smell of burning ozone. Look for high CRI, color rendering index. If the CRI is low, your beautiful walnut project will look like a muddy piece of plastic. You want a CRI of 90 or higher.
That's a huge tip. I've bought cheap lights before, and everything in the room just felt gray, like the life had been sucked out of the paint.
It's because cheap LEDs skip parts of the light spectrum. They give you white, but it's a lie. A high CRI light shows the colors as they really are. Second, do the math. Length times watts per meter, add 30% for your power supply.
And check the polarity. Red is plus, black is minus. Sounds simple, but in the dark, under a desk, with your neck cramping, it's easy to swap them.
I once spent 2 hours troubleshooting a dead strip only to realize I'd soldered the connector on backward. I felt like a first-day apprentice. The LED won't blow up if you reverse the polarity. It's a diode after all, it just blocks the current. But it sure will make you feel stupid.
And finally, heat sinking. People forget LEDs get warm. If you stick a high-power strip directly to wood, the heat has nowhere to go.
It'll cook the adhesive right off. You'll come in the next morning and find your lights hanging off the shelf like a molting snake. Use aluminum channels. They look professional. They diffuse the light so you don't see those annoying dots. And they act as a radiator for the heat.
So, we've covered forward voltage, the 20% margin, voltage drop, and the importance of not treating your circuit breaker like a suggestion.
It's about respect, really. Respect for the physics. Woodworking is about working with the tree. Electronics is about working with the flow of the universe. You can't bully an electron into going further than it wants to. You have to give it the right path.
That's surprisingly deep for a guy who just admitted to making a purple light.
Hey, every mistake is just a design feature in progress. But when it comes to electricity, I'd rather my features not involve the fire department.
Fair enough. Next time, can we talk about why you have 17 different types of glue and yet somehow still use the wrong one for every project?
That's a different kind of sticky situation, Alex.
Thanks for the light, Tiger.
Anytime. Just remember, measure twice, calculate the wattage once, and keep your wires tidy.